Hello students, welcome to EPG Pathshala. I am Professor P03 from the University of Jammu. Today we are going to discuss about a module entitled Motion of Electrons in a Periodic Potential under paper crystallography and crystal growth. In this module, motion of electrons in a periodic potential is described and discussed. Significance of translational periodicity in a crystalline solid is explained. Sommerfeld's model, where electron is assumed to travel in a potential which is constant everywhere inside the metal, is described. The concept of de Broglie waves or Sommerfeld waves or Bloch waves are given. The kinetic energy of the electron is shown to be proportional to the square of the wave number, and the module leads to a relationship between energy and wave vector for a free electron that is of parabolic type. The Bloch theorem is explained. Cronin-Penny model describing the motion of electrons in a periodic potential is explained. The model is shown to lead to energy versus wave vector for electron in a periodic potential as being discontinuous, with discontinuities occurring at k equal to plus minus n pi by a. The concept of brilliant zones is given and their significance in crystallography is discussed. Now, motion of electrons in a periodic potential. Atoms in a crystalline solid are positioned at regular intervals, because of which it exhibits periodicity in the arrangement of atoms in all dimensions. On account of this periodicity, it exhibits various types of symmetries, and as such, the atoms or molecules composing the solid are always related by some symmetry elements. Crystalline solids exhibit various types of physical properties which are structure sensitive. So the physical behavior of crystalline solids cannot be explained unless we have a sound background of crystallography. The symmetry elements have already been discussed in the previous sections. It is essential to describe the significance of symmetry in crystalline solids, or so far as its relevance to the development of theory in the understanding of their physical properties is concerned. One of the physical properties is that of conduction in crystalline solids. Metals have been considered as being composed of atoms with their valence electrons roaming freely inside the solid. The classical theory considered these electrons as moving freely inside the solids like molecules of a gas in an enclosure. Drude and Lorentz theory assumed that these electrons behave like classical particles, move in a constant potential field, and as such applied Maxwell-Boltzmann statistics to understand and explain the behavior of solids. However, it was modified by Sommerfeld by applying quantum mechanical concepts which could explain some of the physical properties of solids. The free electron theory, however, could not explain as to why some solids are good conductors like metals, some semiconductors, or insulators. It is in situations of this type that crystallography in general and periodicity of crystals in particular become significant in the development of solid state theory. significance of translational periodicity. We may select some function, say fr, in the direct lattice space. It is well known that atoms exhibit translational periodicity in a crystalline solid, and because of this fact, this function is also expected to be periodic in the sense that it should be the same at physically equivalent points in the crystal lattice. The periodicity of the function fr could be expressed as f as a function of r vector plus capital R vector is equal to f small r vector, which is identified as equation 1. For all points located at r vector, the vector capital R, by virtue of translational periodicity, is represented by r vector equal to LA vector plus MB vector plus NC vector, where L, M, N are integers and A vector, B vector and C vector are translational periodicities along X, Y and Z directions. Let us start with a one-dimensional case for the sake of convenience and simplicity of mathematical treatment, and represent the equation for one-dimensional case as f as a function of x plus a is equal to f as a function of x as given by equation number 23.2. Since the function of equation 23.2 is periodic, it may be expressed in the form of Fourier series. The expression of equation 23.2, if expressed in the Fourier series form, can be written as f within brackets x is equal to summation sign over n, capital F subscript n raised twice pi I n x by a, which is given as equation 23.3, where n is an integer, a is period of the function. We may express equation 23.3 as f within brackets x equal to summation over phi, capital A phi, e raised exponential of I phi x, where modulus of phi n vector is equal to n into twice pi by a, as is given by equation 23.4. The phi's represent the reciprocal lattice vectors for the linear lattice in one dimension. The Fourier coefficients a subscript phi in equation 23.4 are given by capital A subscript phi is equal to 1 upon a integration within the limit 0 and a f bracket x exponential of minus I phi x dx, as given by equation 23.5. In terms of the Fourier coefficient, the left-hand side of equation 23.2 may be expressed as f within brackets x plus a is equal to summation over phi of capital A subscript phi exponential of I phi x plus a, given as equation 23.6, which will be equal to summation over phi capital A subscript phi exponential of minus I phi x into exponential of I phi a. Making substitution for phi from equation 23.4 gives us exponential of I phi a is equal to exponential of I n into 2 pi by a into a, which is equal to exponential of twice I n pi, which is equal to 1. Or f within brackets x plus a is equal to summation over phi capital A subscript phi exponential of I phi x is equal to f within brackets x using equation 23.4. It shows that the function f within brackets x is equal to summation over phi capital A subscript phi exponential I phi x. We may extend the expression 23.2, 23.3, and 23.4 to the more general case by considering lattice periodicity along the three orthogonal axes, which may be represented by modulus A vector, B modulus B vector, and modulus C vector. In that case, we have, on using equation 23.1, f within brackets small r vector plus capital R vector equal to f within brackets small r vector plus L A vector plus M B vector plus N C vector is equal to f within brackets R vector, given as equation 23.8. As in the case of one dimensions, the expression for three dimensions may be written as f within brackets small r vector is equal to summation over phi 1 vector, phi 2 vector, phi 3 vector, capital B within brackets phi 1 vector, comma phi 2 vector, comma phi 3 vector into exponential of I phi 1 plus phi 1x plus phi 2y plus phi 3z, given as equation 23.9. Equation 23.9 may also be written in the form f within brackets small r vector is equal to summation over phi vector capital B phi exponential of I capital A vector into r vector, given as equation 23.10, where phi vector is the reciprocal lattice vector with components phi 1, phi 2, and phi 3 along the x, y, and z axes. As in the one-dimensional case above, here also exponential of I phi vector into capital R vector is equal to exponential of twice pi in equal to 1, which leads to expression f within brackets small r vector plus capital R vector is equal to summation over phi capital A subscript phi into exponential of I phi vector within brackets capital R vector plus small r vector, which will be equal to summation over phi capital A phi exponential of I phi vector within brackets small r vector, which is equal to f within brackets small r vector, which is in agreement with equation number 23.1. The de Broglie waves, also known as Sommerfeld waves or Bloch waves, insofar as motion of electrons in a crystalline solids is concerned, are expressed in terms of the wave vector. We know capital E is equal to P2 by 2m. Since P is equal to h by lambda, E is equal to h2 upon twice lambda 2m. Substituting this expression for E in the above equation, we get K is equal to twice pi by lambda. Therefore, K is a vector whose magnitude is twice pi by lambda and whose direction is the same as the direction of propagation of electron wave or the de Broglie wave, that is the Sommerfeld waves or Bloch waves. It is also called wave vector or wave number. The kinetic energy of the electron is proportional to the square of the wave number, and the relationship between E and K for a free electron is parabolic as shown in figure 23.1. Bloch theorem. What has been discussed above is regarding general functions with the periodicity of the lattice. It is general case of any such function. We shall now consider here a specific function of periodic potential. We know that the atoms in a crystalline solid are positioned in regular periodic arrays, and as such, the electrostatic potential exhibited by them is also periodic, which may be expressed as V r vector plus capital R vector is equal to V small r vector, given here as equation 23.11. For all Bravais lattice vector R, the potential assumes significance when we deal with the understanding of motion of electrons in a crystalline solid. The periodicity of the electrostatic potential capital V is of the order of 1 angstrom, which is almost the same as the wavelength of an electron as assumed in the Sommerfeld's free electron model for motion of electrons in a crystalline solid. On account of this nearness between the sizes of the electron wavelength and the periodic potential, the use of quantum mechanics in understanding the motion of electrons in a crystalline solid becomes necessary. However, it is assumed here that the crystal is free from any imperfection, which is rather an ideal concept. The real crystalline solid is not free from any imperfection, because of which the periodicity breaks down in the region around imperfections. The imperfections influence the physical properties of crystalline solids. However, it is necessary to assume that we are dealing with an ideal crystalline solid. In order to be able to develop the theory regarding physical properties of solids in the background of symmetries and periodicity in crystals, it is this ideal crystal that we shall consider the motion of electrons as represented by one electron potential Vr, which follows the expression number 23.11 for an ideal crystal, that is capital V as a function of r vector plus capital R vector equal to V small r vector. The motion of electrons is described by Schrödinger equation h psi is equal to minus h cross square upon twice m del square plus V as a function of r vector into psi is equal to E psi, that is given as equation 23.12, where capital H stands for Hamiltonian, m is the effective mass of the electron, h cross is equal to h by 2 pi, where h represents Planck's constant, psi is the wave function, del square is the operator, del 2 upon del R2, and capital E is the total energy. In order to describe the motion of the electrons in crystalline solid, equation 23.12 is required to be solved with the periodic potential of an ideal crystal lattice. Capital V as a function of small r vector plus capital R vector is equal to capital V as a function of small r vector. The solution of this equation is given by psi subscript k within brackets small r vector is equal to capital V subscript k within brackets small r vector exponential of I k vector dot r vector, which is represented as equation 23.13, where capital V subscript k within brackets small r vector plus capital R vector is equal to V subscript k within brackets small r vector, which is represented as equation 23.14. Functions of the type of equations 23.13 are called block functions. K, the wave vector, which is equal to lambda upon 2 pi. It was Bloch who 1928 showed that the solutions are of the form as given by equation 23.13. From equations 23.13, 23.14, we have psi subscript k within brackets small r vector plus capital R vector is equal to exponential of I k vector dot r vector psi subscript k within small brackets r vector, which is given as equation 23.15. Block function can also be expressed by the following equation by selecting eigenstates of capital H in such a way that corresponding to each psi there is a wave vector small k, so that psi as a function of small r vector plus capital R vector is equal to exponential of I k vector dot r vector into psi as a function of r vector. This as equation 23.16 for all possible Bravais lattice vectors capital R. Referring to Schrodinger's equation number 23.12, its solution is given by psi within brackets small r vector is equal to f within brackets small r vector into u within brackets small r vector, which is put as equation number 23.17. Where u within brackets small r vector is a periodic function. Since the potential u as a function of r small r vector is periodic, all the quantities associated with the electron are also periodic. The quantity modulus of psi within bracket small r square has also to be periodic, provided f as a function of r vector satisfies the condition modulus of f within brackets r vector plus capital R vector square is equal to modulus of f r vector square, which is given as 23.18. The solution of this equation is expressed to be of this form: psi as a function of r vector is equal to u as a function of small r vector into exponential of I k vector dot r vector. Put it as equation 23.19. This equation represents Bloch theorem. If one considers the periodicity of atoms in a crystalline solid, it is obvious that the electron moves in the field of periodic potential. For example, figure 23.2 indicates the qualitative form of the electrostatic potential energy of conduction electrons in the field of positive ion cores of monatomic linear lattice. The ion cores left out by conduction electrons are positively charged. The potential energy of an electron in the field of these positive ion cores is negative. Cronin-Penny model. Here we consider the motion of electrons in a simple one-dimensional periodic potential and the Bloch theorem to understand about the allowed and forbidden electronic energy bands in a one-dimensional lattice. For the purpose, we shall consider Cronin-Penny model in which the potential energy variation is assumed to be of the form as shown in figure 23.3. It shows an ideal periodic square well potential used in Cronin-Penny model to illustrate the general characteristics of the quantum behavior of the electron in periodic lattices. The essential features of the behavior of electrons in a periodic potential may be studied by considering the model first discussed by Cronin Penny in 1931 and so is named after him. In this model, it is assumed that the potential energy of an electron moving in one-dimensional perfect crystal lattice is represented in the form of a periodic array of rectangular wells as indicated in the figure, the period of potential being small a plus small b. In regions ranging theta less than or equal to x less than or equal to small a, potential energy is assumed to be zero, whereas in the regions ranging minus b less than x less than 0, the potential energy is V naught. Each of the potential energy may be treated as a rough approximation for the potential in the vicinity of an atom. With this infinite one-dimensional rectangular well potential, it is possible to obtain an exact solution of the Schrödinger equation. Although it is somewhat an idealized periodic potential, which in reality is just a crude approximation to what in reality exists in the real crystal. It is nevertheless very useful because it serves the purpose of illustrating the most explicit way with the help of which several important characteristic features of the quantum behavior of electrons in a periodic lattice can be described. As shown in figure 23.3, capital V is equal to 0 for x lying between 0 and a, and capital V is equal to capital V subscript 0 for x lying between minus b and 0, which is expressed by equation 23.20, and capital V as a function of x plus a plus b is equal to capital S as a function of x, which is given as equation 23.21. So, the periodicity of the potential as represented by the figure is within brackets a plus b. The Schrödinger equation for the two regions are given by d2 psi by dx2 plus twice m by h cross square into capital E psi within brackets x equal to 0 for 0 less than x less than a, represented as equation 23.22. d2 psi upon dx2 plus twice m by h cross square into capital E minus v0 into psi x is equal to 0 for x lying between minus b and 0 as given by equation 23.223. Here it may be assumed that the energy capital E of the electrons is smaller than B0, that is, E is less than V0. We also put two real quantities, alpha and beta, by alpha square equal to twice m capital E upon h cross square and beta square equal to twice m into V naught minus E upon h cross square, which is represented by equation 23.24. E less than V naught because alpha and beta are real quantities. If E is greater than V naught, then beta will be imaginary. The Schrödinger equation, represented by 23.22 and 23.23, may be written as d psi by dx2 plus alpha square psi x equal to 0 for 0 less than x less than a, given as equation 23.25. d2 psi upon dx2 minus beta square psi x is equal to 0 for minus b less than x less than 0, which is given as equation 23.26. From Bloch theorem, we know that the solution of wave equation for a periodic potential will be of the form of a plane wave modulated with the periodicity of the lattice of the form psi x is equal to exponential of ikx into ukx, represented as 23.27, where ukx is the periodic function in x with the period within brackets a plus b, or d psi as a function of x by dx is equal to ik exponential of ikx into uk within brackets x plus exponential of ikx into duk upon dx, which is represented as equation 23.28. d2 psi by dx2 will be equal to ik into ik exponential of ikx into ukx plus ik exponential of ikx duk upon dx plus ike raised to ikx duk upon dx plus exponential of ikx d2uk upon dx2, which will be equal to minus k square exponential of ikx ukx plus ike raised to ikx duk by dx plus ik exponential of ikx duk upon dx plus exponential of ikx into d2 uk upon dx2, which will be equal to minus k square exponential of ikx ukx plus twice ik exponential of ikx duk upon dx plus exponential of ikx into d2 uk upon dx2, which is represented by equation 23.29. Substituting from equation 23.27 and 23.29 in equation number 23.25, we get minus k square exponential of ikx uk as a function of x plus twice ik exponential of ikx duk upon dx plus exponential of ikx d2 uk upon dx2 plus alpha square exponential of ikx into ukx equal to 0 for 0 less than x less than a. For the sake of convenience, let us drop the subscripts and write the above expression as d2u by dx2 plus twice ik du by dx plus alpha square minus k square into u equal to 0 for 0 less than x less than a, given as equation 23.30. Similarly, substituting equations 23.27 and 23.29 in equation 23.26, we have minus k square exponential of ikx into u plus twice ik exponential of ikx into du by dx plus exponential of ikx d2u by dx2 minus beta square exponential of ikx into u equal to 0, or d2u upon dx2 plus twice ik du by dx minus within brackets beta square plus k square into u is equal to 0 for minus b less than x less than 0, which is given as equation 23.31. Representing the value of ux in the interval 0 less than x less than a by u1x and in the interval minus b less than x less than 0 by u2x, equations 23.30 and 23.31 may be written as d2u1 upon dx2 plus twice ik du1 upon dx plus within brackets alpha square minus k square into u1 equal to 0 for 0 less than x less than a, which is given as 23.32. Similarly, d2u2 upon dx2 plus twice ik du2 upon dx minus within brackets beta square plus k square into u2 is equal to 0 for minus b less than x less than 0, which is given here as equation 23.33. The differential equations represented by numbers 23.32 and 23.33 are easily solved by the standard procedure as follows. In solving these differential equations, it is assumed that the solution is of the form u is equal to exponential of mx, so that du by dx is equal to m into exponential of mx, and dtu by dx2 is equal to m square into exponential mx, which is given here as equation number 23.34. Substituting it in equation number 23.32, we get m square exponential of mx plus twice I k m exponential of mx plus alpha square minus k square into exponential of mx is equal to 0 for 0 less than x less than a, or m square plus twice I k m plus within brackets alpha square minus k square is equal to 0. So m is equal to minus twice I k plus minus within square brackets minus 4 by k square minus 4 into alpha square minus k square raised to 1 by 2 upon 2, which is equal to minus twice I k plus minus square bracket minus 4 alpha square raised to 1 by 2 upon 2, which is equal to minus twice I k plus minus twice I alpha by 2, which comes out to be minus I k plus minus I alpha. That is, m1 is equal to I into alpha minus k, and m2 is equal to minus I into alpha plus k. Hence, the general solution of equation 23.32 is u1 equal to capital A into e exponential of m1x plus capital B into exponential of m2x, which is equal to capital A into exponential of I into alpha minus kx plus capital B into exponential of minus k into alpha plus k into x for 0 less than x less than a. Put it as equation 23.35. Following a similar procedure and substituting values of equation 23.34 in equation number 23.33, we get m square exponential mx plus twice ik m exponential mx minus within brackets beta square plus k square exponential mx equal to 0 for minus b less than x less than 0, or m square plus twice I k into m minus beta square plus k square is equal to 0. M is equal to minus twice I k plus minus square bracket minus 4k square plus 4 into beta square plus k square raised to 1 by 2 upon 2 by 2, which is equal to minus twice ik plus minus twice beta by 2 comes out to be equal to minus ik plus minus beta. That is, m1 is given by beta minus ik and m2 is equal to minus beta plus ik. Hence, the general solution for equation 23.33 is u2 equal to capital C exponential of m1x plus capital D exponential of m2x, or u2 is equal to capital C into exponential of beta minus ik into x plus capital D exponential of minus beta plus ikx for minus b less than x less than 0, given in equation 23.36, where capital A, capital B, capital C, capital D are arbitrary constants. These constants are chosen in such a manner that the following four conditions are satisfied. That is, u subscript 1 into x at x equal to 0 is equal to u2 within brackets x at x equal to 0, given as equation 23.37a. One could also write it as u2 within brackets 0 is equal to u2 within brackets 0. du1 by dx at x equal to 0 comes out to be equal to du2 by dx at x is equal to 0, which is given as equation 23.37b, and u1 x at x is equal to a is equal to u2 x at x equal to minus b, which is given here as 23.38a. One could also write it as u1a is equal to u2 minus b. du1 by dx at x equal to a is equal to du2 by dx at x equal to minus b, as is given by equation 23.38b. The first two conditions under equations 23.37a and 23.37b are imposed because of the requirements of continuity of the wave functions. Because of continuity at x is equal to 0, the two wave functions and their derivatives must have the same value at x is equal to 0. The other two conditions, namely 23.38a and 23.38b, are required because of the periodicity of u k as a function of x. Thus, the function ukx should have the same value at x equal to a and x equal to minus b. Imposition of the first two conditions, that is 23.37a and 23.37b, in equations 23.34 and 23.36 leads to u1 within brackets x at x is equal to 0 is equal to a into exponential 0 plus b exponential 0 is equal to u2 x at x equal to 0 is equal to capital C exponential 0 plus d exponential 0, or capital A plus capital B is equal to capital C plus capital D, as is given by equation 23.39, and I into alpha minus k into capital A minus I into alpha plus k into capital B is equal to beta minus ik into capital C minus beta plus ik into capital D, as represented by equation 23.40. The derivation of equation number 23.40 is given as under. du1 by dx is equal to capital A exponential of I alpha minus kx into curly bracket I into alpha minus k curly bracket close plus beta into exponential of minus I into alpha plus kx into curly bracket minus I into alpha plus k curly bracket close. du1 by dx at x equal to 0 is equal to I into alpha minus k into capital A minus I into alpha plus k into capital B. Similarly, from equation 23.36 we have du2 by dx is equal to capital C exponential of beta minus ik into x into beta minus ik plus capital D exponential of minus beta plus ikx into minus of beta plus ik, or du2 by dx at x is equal to 0 is given by within brackets beta minus ik into capital C minus beta plus ik into capital D. du1 by dx at x equal to 0 is equal to du2 by dx at x is equal to 0. So I into alpha minus k into capital A minus I into alpha plus k into capital B is equal to beta minus ik into capital C minus beta plus ik into capital D. Equation 23.40 is thus derived here. Moving forward, we have imposition of the next two conditions 23.38 A and B in equations 23.34 and 23.36. We have u1 at x is equal to a is equal to capital A into exponential of I into alpha minus k into small a plus capital B into exponential of minus I into alpha plus k small a. u2 at x is equal to minus b is equal to capital C into exponential of minus beta minus ik into small b plus capital D into exponential of beta plus ik into small b. So, capital A exponential of I into alpha minus k small a plus capital B exponential of minus I into alpha plus k into small a is equal to capital C exponential of minus beta minus ik into small b plus capital D exponential of beta plus ik into small b, which is represented by equation 23.41. And I into alpha minus k capital A into exponential of minus I alpha minus k a minus I into alpha plus k capital B into exponential of minus alpha plus k into a is equal to beta minus ik into capital C exponential of minus beta minus ik into small b minus within brackets beta plus ik into capital D exponential of beta plus ik into b, given as equation 23.42. Thus, application of 23.37 AB on equation number 23.34 and 23.36 leads to four linear homogeneous equations in the constants capital A, capital B, capital C, and capital D. The coefficients capital A, capital B, capital C, and capital D can thus be determined as the solution of a set of these four simultaneous linear homogeneous equations in these quantities. There is no solution other than capital A equal to capital B equal to capital C equal to capital D equal to 0 unless the determinant of the coefficients vanishes. That means these four equations represented by 23.39 to 23.42 have a solution only if the determinant of the coefficients of capital A, capital B, capital C, and capital D vanishes. That means the determinant of 1 I into alpha minus k exponential I into alpha minus k into u I into alpha minus k exponential of I into alpha minus k into small a and 1 minus I into alpha plus k exponential of minus I into alpha plus k by 2 minus I into alpha plus k exponential of minus small a plus k into a. Then minus 1 minus beta minus ik minus exponential of minus 5 minus ik into small b minus beta minus ik exponential of minus beta minus ik into b. The fourth column is minus 1 beta plus ik minus exponential of beta plus ik into small b beta plus ik into exponential of beta plus ik small b is equal to 0, which is given here as equation 23.43. On expansion of this determinant, one can show after rigorous and straightforward algebra that equation 23.43 can be expressed as beta square minus alpha square upon twice alpha beta sin beta b sin alpha a plus cos beta b cos alpha a equal to cos a k into a plus b. Put it as equation 23.44. In order to obtain a more convenient equation, Cronin and Penny considers the case for which the potential barriers become delta functions. That is, V subscript 0 tends to infinity and small b tends to 0, but the product V subscript 0 into small b or beta 2 into small b remains finite. Such a function is known as delta function. Under these circumstances, equation 23.44 reduces to beta upon twice alpha into 2b sin alpha a plus cos alpha a is equal to cos ka, given as equation 23.45. It is because when b tends to 0, sin beta b tends to beta b and cos beta b tends to 1. And because E is less than V0 and V0 tends to infinity, so E is very small. Alpha 2 may be neglected, but beta cannot be neglected on account of involvement of the term V0 minus E. Equation 23.45 can be further expressed as beta square AB upon twice alpha A into sine alpha A plus cos alpha A is equal to cos Ka. Let us put beta square AB upon 2 equal to P in the above equation. We get P dot sine alpha A upon alpha A plus cos alpha A equal to cos Ka. Put it as equation 23.46. The quantity capital P is defined by the expression capital P is equal to beta square AH upon 2 is equal to twice m v naught AB upon twice h cross square is equal to m v naught AB upon h cross square. It means that the solutions for the wave functions exist only if equation 23.46 is satisfied. We are now in a position to define the quantity capital E. Since V naught tends to infinity, that is capital P is a measure of the area V naught B of the potential barrier. The physical significance of this quantity is that if capital P is increased, the area of the potential barrier is also increased, and so a given electron is bound more strongly to a particular potential well. When P tends to 0, the potential barrier becomes very weak, which in other words means that electrons are free electrons. When P tends to 0, that is for free electrons, expression at 23.46 can be written as cos alpha A equal to cos Ka, or alpha A is equal to Ka. From equation 23.24, we know that alpha square is equal to twice me upon h cross square. So alpha square is equal to twice m upon h cross square is equal to k square. So E is equal to k square h cross square upon 2m is equal to h square k square upon 8 pi 2m on substitution for h cross equal to h by 2 pi, which is represented as equation 23.47. The expression at 23.47 resembles the result as was obtained by considering the Sommerfeld model of metal. A plot of the function p sine alpha by alpha a plus cos alpha a when drawn against alpha a for p equal to 3 by 2 appears as is shown in figure 23.4. We know that alpha is equal to twice m capital E upon h cross square raised to 1 by 2, which suggests that alpha square is proportional to energy capital E. The abscissa theta, which is a measure of energy, and in order to calculate the energy represented by the function at a point, the value of alpha A corresponding to that point is determined. The values of alpha A, which satisfy equation 23.46, are found out by drawing a line parallel to alpha A axis at a distance cos Ka from it. If Ka is continuously varied from 0 to pi, that is cos Ka from plus 1 to minus 1, one is able to find all possible values of alpha A and hence that of energy. It is important to realize that the right hand side of equation 23.46 can accept only values between minus 1 and plus 1. That is Ka continuously varying from theta to pi and cos Ka from plus 1 to minus 1 as indicated by the horizontal lines in the figure. Therefore, the condition as imposed by equation 23.46 can be met only by the values of alpha A for which the left-hand side lies between plus minus 1. In figure 23.4, we have plotted the left side of equation 23.46 as a function of alpha A for the arbitrary value capital P equal to 3 pi by 2. As the cosine term on the right side can have values between plus 1 and minus 1, only those values of alpha A are allowed for which the left side falls in this range. The allowed ranges of alpha A are indicated in the figure, and through the relation alpha equal to twice me upon h cross square into 1 by 2, they correspond to allowed ranges of the energy capital E. The boundaries of the allowed ranges of alpha A correspond to the values n pi by A for k. It is usually restricted to the domain minus pi by A less than or equal to k less than or equal to plus pi by A, which is known as the first brilliant zone. The E-K diagram showing the allowed and forbidden energy bands are shown in figures 23.5 and 23.6. At the zone boundaries, that is k equal to plus minus pi by A, the block wave function satisfies the Bragg condition, and the group velocity, which is given by 1 upon h cross into dE by dk, is 0, which corresponds to standing wave. Let us analyze the details of what may be concluded from the figure drawn on the basis of equation 23.46. Number 1. There are infinite number of allowed energy bands separated by intervals in which there are no energy levels. Such regions are known as forbidden regions. The boundaries of the allowed ranges of alpha A correspond to the values for which cos Ka is equal to plus minus 1. That happens if Ka is equal to n pi or k is equal to n pi by A, where n is equal to 1, 2, 3, etc. Second, the first term in the expression for f alpha A, that is p dot sine alpha A, decreases on an average with increasing alpha A. It suggests that the width of the allowed energy bands increases and the forbidden regions get narrower as alpha A increases or as energy increases. Number 3. As capital P increases, the width of the allowed band decreases. Increase in the value of capital P means the increase in binding energy of the electrons. In the extreme case, when capital P is infinite, the allowed energy bands get infinitely narrower. Consequently, the energy spectrum becomes line spectrum and are independent of K. If P tends to infinity, the allowed energy ranges of alpha A reduce to points given by alpha A is equal to plus minus n pi, or alpha is equal to plus minus n pi by A, or alpha square is equal to n square pi square upon A square. Substituting it for alpha equal to twice me upon h cross square raised to 1 by 2, alpha square is equal to twice me upon h cross square is equal to n square pi square upon A square, or capital E is equal to n square pi square h cross square upon twice ma square, as is given by equation 23.48. It shows that capital E is independent of K. The energy levels in this case are discrete and the electron is completely bound. It is trapped within the potential wells and moves only in one cell of width small a. From the discussion on analysis of equation 23.46, we come to the conclusion that in the one-dimensional problem, for the limiting case, the spectrum of energy values that are permitted is found to be consisting of continuous regions separated by finite intervals. By varying the quantity capital P, that is V naught B, from 0 to infinity, we move from the case of free electrons to that of bound electrons and so are able to study the changes in the allowed and forbidden ranges of energy and the wave function. We may also use equation 22.46 to study the variation of energy capital E. With the wave number k, the variation is as shown in figures 23.5, 23.6. From these figures, one arrives at the following conclusions. Number one, the energy spectrum of the electrons consists of a number of allowed energy bands separated by forbidden regions. Second, the width of the allowed energy bands increases with increase of energy values. Third, if V0 is made 0, the E versus K curve becomes a continuous parabola, the same as that of free electrons as shown in figure 23.1. Number 4. There are discontinuities in the capital E versus K curve which occur for K equal to n plus minus n pi by A, where n is equal to plus minus 1, plus minus 2, plus minus 3. The range of allowed values of k between minus pi by a and plus pi by a constitutes the first brilliant zone. The range of values of k between minus pi by a and minus 2 pi by a and between plus pi by a and plus 2 pi by a constitute the second brilliant zone. The energy capital E is represented as a function of for phi is equal to 3 pi by 2. Analyzing the curve of capital E against K further regarding the discontinuities in the E versus K at K equal to n pi by A, where n is equal to 1, 2, 3, etc. The K values define the boundaries of the first, that is number 1, second, that is 2, third, that is 3, and so on, brilliant zones. Figures 23.5 shown here provides only half of the EK curve. The first zone, in fact, extends from K equal to minus pi by A to plus pi by A. Similarly, the second brilliant zone is composed of two parts, the one extending from plus pi by A to plus 2 pi by A, as shown in the figure, and the other part extending from minus pi by A to minus 2 pi by A. Figure 23.6 represents the full E-K curve. We may call each position of the curve as a band. The curve of E-K has the following characteristics. Number 1, the curves are horizontal at the top and bottom. Number 2, the curves are parabolic near the top and the bottom, having curvatures in opposite directions. Number 3, d2e by dk2 is positive in the lower portion of the band and negative in the upper portion of the band. Let us consider a linear lattice of lattice constant small a. According to free electron theory, capital E versus wave vector k is continuous, as is shown in figure 23.1. The low energy part of the band structure is shown in figure 23.7 for electrons which are nearly free but with an energy gap at wave vector k is equal to plus minus pi by a, resulting into creation of forbidden gap as a result of our assumption that electron is moving in a periodic potential, unlike in the case of free electron theory where electron is assumed to be moving in a constant potential field. The curve of capital E versus wave vector k for an electron in a monatomic linear lattice with lattice constant small a appears as shown in figure 23.7. The energy gap E subscript G is associated with the first Bragg reflection at k equal to plus minus pi by a. The Bragg condition in terms of the reciprocal lattice implies that k vector plus g vector square is equal to k vector plus g vector dot k vector plus g vector is equal to k square for diffraction of a wave vector k, if taken in one dimension, becomes, on expanding the dot product and simplifying, twice k vector dot g vector plus g square equal to 0, which is given here as equation 23.49, where capital G is 2 pi times a vector from the origin to a lattice point of the reciprocal lattice, and k is a vector of magnitude twice pi by lambda along the direction of the incident X-ray beam. Equation 23.49 is the vector form of the Bragg equation. In one dimensions, equation 23.49 becomes k equal to plus minus 1 half of capital G, which is equal to plus minus n pi by small a, given as equation 23.50, where capital G is equal to plus minus twice n pi by a is the reciprocal lattice vector. The first reflection and the first energy gap results at k equal to plus minus pi by a. Other energy gaps result for other values of integer in equation 23.50. The reflection at the wave vector k equal to plus minus pi by a takes place because the wave reflected from one atom in the linear lattice meets constructive interference with the wave from a nearest neighbor atom. The phase difference between the two reflected waves is plus minus twice pi for these two values of k. The region in the k space between minus pi by a and plus pi by a is called the first Brillouin zone. Cronin-Penny model has shown that the energy discontinuities in the monatomic one-dimensional lattice result when the wave vector satisfies the relation k is equal to n pi by a, where small n is an integer which may be positive or negative. In the one-dimensional monatomic lattice, a line representing the value of k is divided up by the energy discontinuities into segments of length pi by a, as shown in figure 23.8. These line segments are known as Brillouin zones. The segment minus pi by a less than k less than pi by a represents first Brillouin zone. The two segments minus twice pi by a less than k less than minus pi by a and pi by a less than k less than 2 pi by a form the second Brillouin zone, and so on. Brillouin zones are characteristic of a particular crystal structure, and as such, each crystal structure forms its own characteristic Brillouin zones. Let us take the example of two-dimensional simple square lattice as shown in figure 23.9. The first Brillouin zone for this lattice will be a square A, capital B, capital C, capital D, whose boundaries are defined by kx equal to plus minus pi by a and ky equal to plus minus pi by a. Similarly, the boundaries of the second Brillouin zone are defined by plus minus kx is equal to plus minus ky is equal to pi by a, as represented by the diagram capital E, capital F, capital G, capital H. Now we shall talk about significance of Brillouin zones. Number 1, looking at the curve shown in figure 23.6, one finds that electron energy increases continuously from 0 until the value of k reaches pi by a. Thereafter, it gets stopped as if it meets an obstacle or a wall at that instant and consequently gets reflected. Treating electrons as waves and the propagation of electrons through a crystal as analogous to the propagation of electromagnetic waves, we arrive at a very important conclusion. We know that X-ray will suffer reflection if incident normal to a set of planes of interplanar spacing small a, provided This equation is satisfied. N lambda is equal to twice A sine 90 degrees for X-ray is at right angles to the planes. Therefore, N lambda is equal to 2 for electron, K equal to N pi by A and K equal to 2 pi by lambda. So 2 pi by lambda is equal to N pi by A, or N lambda is equal to twice A, which is the same condition as for Bragg reflection. Thus, we may conclude that electron suffers Bragg reflection when N is equal to plus minus 1 or plus minus 2 and plus minus 3 dash corresponding to first, second, third order reflections and so on. The zones between the values of k equal to minus pi by a and plus pi by a constitutes the first brilliant zone and so on. Second, the zone boundaries represent the maximum energies that the electron can have without developing any discontinuity. Number 3, the energy gap at the zero boundary is called the forbidden zone or band. Electrons cannot have these energies. Number 4, considering velocity of electrons in a periodic potential, given Vg equal to twice pi d nu of dk and capital E equal to h nu, and so Vg is equal to twice pi by h into dE by dk. Slope dE by dk is equal to 0 when k is equal to 0, and dE by dk is equal to 0 when k is equal to pi by a. Therefore, the velocity of electron is 0 both at the bottom and at the top of the first brilliant zone or band. At intermediate regions in the zone, the electron velocity reaches the free electron velocity hk upon twice pi m. Let us now consider the motion of the electron in the first brilliant zone under the continued application of a force capital F, either due to electric field or any other agency. Velocity of the electron at k equals 0 will increase, but when it approaches the value of k close to plus pi by a, its velocity begins to decrease, and at k equal to plus pi by a, the velocity becomes 0, indicating that the electron wave packet suffers a Bragg reflection and begins to travel in a direction opposed to the applied force. The propagation in the negative direction continues until it becomes equal to minus pi by a. Once again, the electron suffers Bragg reflection and the forward propagation starts until value of k reaches plus pi by a. In other words, the electron is shunted back and forth in the first brilliant zone under the application of a constant unidirectional force. It means that a stationary electron wave is set up in the first brilliant zone instead of a traveling wave. An electron remaining in one zone or band cannot cross over to another zone by continuous application of force. Two consecutive brilliant zones are separated by a forbidden energy gap. So, unless and until the electron in the first zone absorbs an energy equal to that of the forbidden gap, in a single dose, the electron cannot cross over to the next brilliant zone irrespective of the duration of the applied force. Number 7. If the electrons continue to move back and forth in their respective brilliant zones, there is no change in the sum of the momenta of all the electrons, and as a result, no net current is produced by the crystal. It obviously means that the material is an insulator. Now suppose the forbidden gap is small enough, or if impurity atoms provide some localized electronic states within the forbidden energy gap, one will find a semiconductor behavior. The third situation is that there is no forbidden energy gap. In that case, there is no restriction for increase in the value of K, and so electric conduction can take place. The material in this case is a good conductor. Now we may summarize of what we have discussed so far. We have discussed motion of electrons, both in a constant potential field, as assumed by Sommerfeld, as well as in a periodic potential, as assumed in Kronig-Penney model. Significance of translational periodicity in a crystalline solid is explained. The concept of de Broglie wave or Sommerfeld waves or Bloch waves are given. It is shown that Sommerfeld's model of motion of free electrons in a constant potential field inside leads to a relation between energy and wave vector for a free electron that is parabolic. Bloch theorem is explained. It is shown that if electron is assumed to travel in a periodic potential as proposed by Croning-Penny model, it leads to energy versus wave vector that shows discontinuities at k equal to plus minus n pi by a. The concept of brilliant zones and their significance in crystallography is explained. Thank you.